Today we are going to see about inductors and inductor is an element that stores energy in association with the flow of current, and this is how an inductor looks like. So the unit of inductance, which is the electrical property of the inductor, is Henry. H. All right. So again, I'm just going back to what I said already. So it's an element, right? So it's a component of the circuit, electrical circuit, and it stores energy, right? So it stores energy in the form of magnetic field, and its presence, right? So unique feature of the inductance is that its presence is felt only when there is a change in current, or the current is changing periodically, right? So the flow of current is the only thing that makes the inductor work. All right, so without the change in current, there is no inductor. So basically an inductor can be used in AC circuits only. So if you are using in DC circuits, inductor is not going to work, right? So it is working in association with the flow of current. Okay, so I'll just draw a basic inductor circuit, a basic inductor here in the bottom. So this is how the basic inductor looks like. And V is the potential difference across the inductor, and I is the current flowing inside the inductor. Now you see this potential difference across the inductor V is proportional to the rate of change of current, di by dt, right? So if you are writing in an exam, you can write this separately. Di by dt is the rate of change of current. You can write it here, right, so that you can use it for taking notes. Rate of change of current. All right, so V is not the supply voltage, it is the induced voltage. Induced voltage. Right, so since I said V is proportional to di by dt, we have to remove the proportional symbol by multiplying a proportionality constant, right? So who comes to the rescue? So V is equal to L di by dt. All right, so L is the proportionality constant and L is the symbol of inductance. So inductance is the proportionality constant here. So inductance, the proportionality constant. Okay, and now can cross multiply and get the value of L. Yes, it's V volts. It's V volts, and L is equal to V dt by di. That is equal to volt second per ampere, or Henry. It's Henry or Henry. Right, now we see from this equation, you can see that if an inductor induces an voltage of 1 volt when there is a current that is uniformly varying at the rate of 1 ampere per second, then it is said to have an inductance of 1 Henry, right? So if they ask you what is 1 Henry, you should tell them that the inductor induces a voltage of 1 volt when there is a uniform changing or uniform variation of current at the rate of 1 ampere per second. That is what you call is 1 Henry, right? So 1 Henry is dash, right? You have to fill it up, right? Now you are integrating the above equation with respect to time, above equation number 1 with respect to time, right? With respect to time, so I is equal to 1 by L integral 0 to t v dt plus I of 0. Alright, so I of 0 is the current at, I'll just write in the bottom, I of 0 is the current, please wait, I of 0 is the current at the time t equal to 0, right? So at the time t equal to 0 means, I just finished writing this, t equal to 0, yes. So the current in an inductor cannot change suddenly at 0 time. If the time is 0, the current is has some value. If the time is 1 second, the current will change its value from the previous value, right? So it cannot change. So the instantaneous power at a given time t, instantaneous power, the power entering into the inductor at the given time t, that is what you call instantaneous power, right? So power at given time t, right? So what is the value formula for power, calculating power? It is the product of voltage and current, right? So V into I is nothing but P, right? So P is equal to VI. VI, so that is equal to, so you have found out the value for voltage previously, you can go back and check it. So that is L di by dt, that is equation 1, right? So that is equation 1, so L di by dt, and you can rewrite this as P is equal to Li di by dt, right? So because when current is constant, the derivative is 0 and there is no additional energy stored in the inductor. When the current increases, right, the derivative is positive and the power is also positive and additional energy is stored in the inductor, right? So that is how this inductor works. So if the current is constant and if you derive the constant, it is going to be 0, right? So we are going to calculate the energy stored in the inductor, right? You used to call it, mention in it as WL, right? So the energy stored in the inductor WL, inductor WL. So W stands for energy and L stands for inductor, right? So WL is an integral of power from the time of the beginning to the end time, right? So time is 0 to t, that is what we are having, and VI is nothing but power. We are integrating with respect to time, all right? So if you are integrating this and you know the value of t, and you have the value of V also, so Li di by dt, that is power with respect to time, and dt and dt they get cancelled, and integrating this, you get integral 0 to t Li di Li dt, I mean sorry, it's Li di, it's not dt, sorry, it's Li di, right? So your taking L outside, because it, as mentioned earlier, it is a constant, proportionality constant, so you cannot integrate or differentiate constants. So take L outside, and if you integrate this, I with limits 0 to t, and it's I squared by 2. So it's 1 by 2 Li square. So this 1 by 2 Li square is very similar to the kinetic energy equation half mv square. So kinetic energy is appearing everywhere when there is a movement of a body, or if there is a force applied to it, right? Half mv square, mass into velocity square. So according to these equations, inductance has no history of previous operation.